Hi, everybody. This is our lecture for the 28th of January, 2026, and it's a relatively short lecture. We're just going to take a look where we are, and then I'm going to show you the bearing that I attempted to find last week, but I have now identified it. So let's take a look at where we are with our schedule. Today, the 28th, we're in week 3. So that means in a perfect world, you will have completed and turned in the homework review, and you will have completed and turned in homework number 1, and you'll be working on homework number 2. If you're behind that schedule, just keep plugging away, because I don't even really mention it until we start getting off track to the point that we're going to suffer for it. The big mark we need to make is that you take this quiz, number 1, after you've completed homework 1, homework 2, and the review, sometime around the end of that week. So sometime before February 15th, and then we'll be on schedule to do the midterm exam the second week in March, so that you can go away on spring break the 2nd of March, not the second week of March. So you can go away on spring break the second week of March and have a nice time and not have to worry about your homework. So when we take a look, we talked about chapter 1 last week, and I recorded a video, and one of the things that was brought to my attention was that the audio did not start until about 9 minutes in. So if you do watch the video from last week, just remember that the first 9 minutes are just me flashing pictures of bridges on the screen. So you won't miss any content, but it's not very exciting under most circumstances. So when we start talking about chapter 2, what is the topic that we are going to be covering? Okay, we're going to be talking about stress and strain axial loading. And the first thing I'd like to bring up is, often in everyday conversation, stress and strain are used synonymously. You know, you're under a lot of strain, you're under a lot of stress. In mechanics and materials, they mean very different things, and they don't mean any of that stuff. So what a stress is a force per area, whether it's a normal force, an oblique force, or a transverse force. You'll have normal stress, oblique stress, shearing stress. Okay, so it's always in units or dimensions of force per area, pounds per square inch, Newton per meter squared, which is the Pascal, and so forth. Strain, which we've not introduced to this point, is the deformation that occurs based upon a stress. So for example, if you pull on something, it gets a little bit longer. Okay, the stress is the percent of elongation. If you compress it, it's the percent of contracture. And if you put it in torsion, it would be measured in an angle.
That's strain?
That's strain.
So like 100% strain would be like it's doubled in size.
Exactly, that's
Okay.
exactly right.
Okay,
That's exactly
It's
right.
probably snapped in half by then, but
That's right.
Yeah.
That's exactly right. So this, and I love this, and I actually love to draw this, so I'm sad that I won't get to draw it on in this particular format. But when we talk about normal stress under axial loading, like we said, you have something, you pull on it and it elongates, and that percent of elongation is called the strain. The symbol for, okay, so there's 2 symbols. If you look at this one, this is a small delta, which is like this. Delta is not the strain, but delta is the inches or feet, the amount of deformation. If you take delta and divide it by the original length, that is called epsilon, and epsilon is the strain. So you can see that the dimensions of this are going to be length, and the dimensions of this are length. So epsilon or strain is dimensionless. Okay, when we talk about shearing stress, you talk about maybe taking something like this and putting it under stress, it's going to deform like this. And so the change in the angle from the original to the new angle is called gamma, which is a shearing strain. We're not going to mathematically do a shearing strain right off the bat, but in any case, strain is dimensionless fraction or percent change in either in shape, in either length or in angle. And when you start working these problems, the only thing that I would like to tell you, the numbers should be very small, right? I mean, you know, generally speaking, when you pull on something, unless it's silly putty or something like that, if you pull on a piece of steel, it's not gonna elongate a lot. So here we have a graph of P, which is that axial load, or I should say del, which is the change in length versus P. And you'll see that we have a straight line for a while, and then we have something where it kind of goes down. So what that means is we're actually decreasing the load that we're applying to it, and we're still getting a stretch. And then we come up to some final point where we actually have rupture, where the structure ruptures. This part of the curve is referred to as the elastic range, where, and if you're in the elastic range, you can rebound. So you stretch it out, if you remain in the elastic range, the structural member will go back to its original size. It will no longer be elongated. But if you exceed the elastic limit, which occurs right here, other things start to happen. And the other things that start to happen are actually characteristics of the material. So you can tell by this graph if it's ductile, if it's brittle, and with closer examination and better data, you can also tell what the material actually is. Okay,
So
yeah,
if we had something like this and it, or like say like you had like a cube that was starting to twist and
Yes.
fracture,
yes.
would it be weaker after that initial deformation too, or?
That's a great question. The answer is sometimes, okay? If it's new and you just stress it a little bit, the answer is no. But even as it gets older, even if you continue just with the same amount of stress, it will become weaker. Those two ideas are referred to as something and creep. But creep basically means over time, something deforms, that it doesn't behave elastically in what you anticipate it to have elastic behavior for. So you actually kind of decrease the ultimate stress that it's called slip and creep. There you go, slip and creep. So you can deform it permanently or weaken it by subjecting it to stress that it should be able to bear in too many cycles, too many times, or just by the structural member getting older. So you'll have that. But while it's new and not subject to too many repeated loading cycles, it should not be weaker and it should not be permanently deformed. So here's our basic equation. Epsilon is equal to del over L, and that's what I've written up on the board. And there's actually a limit, right? So it's not really, if you have something like this, a homogeneous bar, it's pretty much looks like this. If you have something that's less homogeneous, there's going to be other effects that occur that turn it into a limit equations, but we're basically going to deal with just linear elongations for now. All right, so a stress strain diagram, as I said before, is actually a characteristic of a material. So if you see how it behaves under repeated loading and different amounts of stress, you can actually determine what that material is. This is, we have one of these. This is called a tensiometer, and it measures the tension on a structural member. We don't have one here. We have one in the welding shop though. So if you're nice to the welders, they may show it to you, but they just pull and push on things and see how they deform and how they fail and produces a graph.
Don't they do those for like to test their welds and stuff?
They do. That's exactly correct. And to test just raw material and then to test the welded material as well. Yeah. So here are a couple of stress strain diagrams. This is for low carbon steel. This is for an aluminum alloy, a to be determined alloy. But what we basically see here is that you have a straight line portion until you get to a maximum, which is referred to as the ultimate. It's not really it's a yield, excuse me, where the material yields. So sigma y is where it begins to yield. Yielding means that you will actually with less stress, continue to elongate the material until you reach an ultimate. And then if you continue stretching it beyond the ultimate, you'll see that the stress goes down, but that eventually the material will rupture. Low carbon steel is more ductile. Aluminum alloy, you can see that the curve here and here are approximately the same, but they behave very differently. This aluminum alloy just breaks. It just expands a little bit and then it breaks. It does not go through yield. It doesn't go through this idea of strain hardening, which is called strain hardening because it continues to, the strain continues to increase and it begins to accept more stress again. This is where you're getting into trouble. Often, if that starts to happen to a part, it will feel hot. You'll feel there will be heat buildup in it because you're actually changing the metallurgy of the element. And one of the things that happens with a ductile material, ductile, brittle, with a ductile material is when you pull on it and you get it into the yield and the strain hardening regions, you reach ultimate stress, and right before it ruptures, it will start to, they call it necking, where you have a lower diameter, and once again, it'll feel hot, and then it will break. You can also tell this is a very brittle material. This doesn't do anything, right? I mean, it doesn't yield at all. It's just like you pull on it and it breaks and that's it. So, so that is the difference.
Like Chinese.
Yes, there you go. I like it, exactly. So, brittle breaks tend to be at a 90-degree angle from the axis. And if you have a more ductile material, the shape will be a little bit different. So stress strain diagram for concrete. This is very important, especially neither of you is planning to be a civil engineer, but everything is built out of concrete. And the one thing about concrete is concrete behaves very well in compression and it does not behave well in tension at all. So if you put it in tension, it fails. That's the way it works. So you can see that this is unusual in the sense that you pull on it, it ruptures, and if you push it back together, it has a different kind of a curve, but it will eventually rupture in compression. But the rupture in tension occurs at a much lower strain. So if you elongate it a little bit, it ruptures, and you have to compress it or shorten it quite a bit in order to get it to rupture.
So like, say I were designing a building,
Yes.
I would want the concrete to be able to handle the weight of the building, but I don't want it to be trying to account for any sort of like wind forces or anything that might pull it side to side.
That can be, yes. And another thing that you want to do, put this up on the board. We'll study this later on, but it's an excellent question. If you have a concrete slab and it's flat like this, it works very well. If you load it and it bends like this, the top part of it works very well and the bottom part does not, because it goes into tension. So there's a place which they refer to as a neutral axis where the stress is zero, where it shifts from being in compression to tension. So there's some things you can do here to minimize this. And the easiest thing is to put rebar in it. And if you put rebar in it, the rebar will take the tension. Rebar is great in tension. So all that the concrete below the neutral axis really does is hold the rebar in place. And if you have a big building, you can actually pre-stress the rebar. So you put the rebar in the form and then you pull on it before you add the concrete, you let the concrete set, and then you release it and it compresses the bottom part of the concrete.
That's cool.
And then when you, so then when you load it, it's still in compression for a while. So, yeah, those civil engineers, they're clever people, you know? So, anyway, so that is where we're going with chapter 2, and it's 12:50, so I'm gonna stop. But this is once again, this is a stress strain diagram for a different type of a material. But you see the same characteristics. You have a straight line portion, which is elastic, and there's a meaning to the slope of this. You'll find out in a little bit. You get to a yield, and then things start to change. You're actually changing the metallurgy of the substance until it ruptures. So this is ductile and the other one was brittle. So the other part to realize is that ductile to brittle is almost never an absolute, it's a continuum. In other words, things are very ductile or very brittle or intermediately ductile or intermediately brittle, but it's kind of a spectrum. So the last thing I wanted to show you, I'm just gonna come up here to the camera and see if We can show this. This is what we were looking at. This is a gear that was, it kind of blew up, as you can see. But what happens is there is a drift key right here. This was supposed to fail, but for whatever reason, somebody replaced it with something quite strong. So instead of the key failing, the whole thing failed. So you can see the splines are torn up. We have a break right here where this bolt is, and the whole thing is a piece of junk, but it's a piece of instructive junk. So I love it.
That, the shaft is just blowing my mind, the way it
Yeah,
turned it looks like wood.
it does. You know, it really does. That's a very good point. It does look like wood. It just blew up, and I mean, it's just like it's splintered, really.
Yeah.
Yeah. So, and I wish I knew more about it. It was something that somebody gave me. I think my husband gave it to me, but he didn't do this, by the way. He did not put the driftwood key in it. I want to be sure. So, but there we go. All right, guys, have a wonderful day.
He probably found it on